Maybe a little less.
3 weeks ago.
All right, how's everyone doing this morning?
I'm here.
Say again?
I'm here.
Sometimes it's all you can do, and that's important. All right, anyone need anything or have any questions, concerns, etc. before we get started? Yes. Yes. 1:30. It's 1:30 either Monday, Tuesday, or Wednesday, depending on which one you signed up for. But it'll always be the same time each slot, each day. And it's in 126, last door on the right. Anything else for right now? All right, a couple small things, reminders for me. At this point, we're wrapping up what is arbitrarily called Chapter 2 in the course. The chapter numbers are just kind of arbitrary. It's based on the numbering in the textbook the course is based on. What that means is, as we say wrap up one chapter number, then by that point I will have covered everything you would need to be able to comfortably do the homework for that section. And again, as a reminder, the homework isn't due and it isn't graded. It's meant to be practice to make sure that you understand everything that's contained within that chapter and can use the relevant formulas. For example, if we click on Chapter 2 on Brightspace, it'll tell you the numbers of questions you should be able to do from that chapter within the book. But you don't have to actually lug the book around if you don't want to, because I have written down all those questions, and the answers are all in either the back of the book or here on the second document, which does contain the answers for each question. Each question is fairly short. Some of them are just brief concepts, some of them are very short math. It's just the list of things you should be familiar with from the chapter. And again, it is meant to be practice. And student tutoring has started back up, which presents a great place for students to work on it both with each other and also with very qualified math and physics majors here at the school. The physics tutoring, which doubles as math tutoring, is every Tuesday and Thursday, 6 to 8 p.m. in this room. There are very qualified, very wonderful physics majors who come to help out with that. So it's just a great time to be working on your homework, either with classmates or directly with the tutors. Again, you can work with each other on the homework and you have all the answers. It's just practice. Bless you. So, all that said, once again, before I get back to what we were talking about on Monday, any questions about anything I just said before we conclude Chapter 2? All right. Where we left off last time, Chapter 2, we've been talking about Newton's first law and the definition of equilibrium. We began looking at this car. The SUV is driving forward at constant velocity. It weighs 10,000 newtons. Remind me, is this car in equilibrium? Yes. Why is it in equilibrium? Constant velocity, very good. If constant velocity, then equilibrium. If it's in equilibrium, what does that tell us about all the forces acting on the object? They add up to zero. Very good. And technically, constant velocity can mean at rest. It's just the velocity is zero in that case, constantly at zero. So this is kind of this version of the if-then statement I told you on Monday is kind of the more comprehensive version of the two, because at rest and moving at constant velocity are both constant velocity. Either way, the object's in equilibrium, so all the forces on this thing must add up to zero. Remind me again which forces are currently acting on this particular vehicle. Gravity. We can't escape it as long as you're on this planet. Frankly, you can't even escape it off of this planet. Gravity does still exist in space. We know that because the moon still orbits the Earth. The astronauts aren't weightless, they're just constantly falling. What else? Friction. Friction, very good. I'm kind of wrapping up both air resistance and mechanical resistance from the engine and from the road together as just one force of friction. That's all resistive forces trying to stop the vehicle from moving. What else? Normal force from the ground pointing up, very good. We know that this must exist because the car is on a road and the car's weight is not pulling it through the road towards its core. The ground must be supporting the car. What else if this vehicle is at constant velocity?
Force from the engine.
Force from the engine, very good. We discussed how two forces that are equal and opposite must add up to zero together. In the vertical axis, we've got normal force and gravity canceling each other out. In the horizontal axis, we need something mitigating the friction in order to stay at constant speed, and that in this case would be the force from the engine. If you are driving and you have cruise control off, and you take your foot off of the gas, thereby eliminating any force from the engine, what is going to happen to your car? You're going to slow down. And that happens because if the engine isn't going, there's no forward force mitigating all the forces of friction trying to stop you. You have to keep pressing the gas even just a little bit to stay at speed, right? Now, we've been discussing how an object's inertia compels it to keep doing what it's already doing, right? The car wants to keep moving forwards. The fact that the car eventually slows down is not what the car itself actually wants to do. It's doing that because of an outside force, friction. Every object that's moving wants to keep moving. Friction is something outside of that object telling it, hey, I know what you want to do, but I'm going to stop you anyway. Friction's a big pest, if I'm being honest with you. It's the bane of most mechanical engineers. If we didn't have friction, things could keep moving in a straight line forever. We would have perpetual motion if not for friction. Which is why the closest thing you get to perpetual motion is moving in a straight line through space, where there's no friction to stop you. But even then, orbits decay with time. You can't really avoid it. I'm kind of getting off topic, sorry. All that to say, if there's no force from the engine, then we cannot be in equilibrium while friction is present. There has to be something overcoming that friction to keep us moving at constant speed. A single non-zero force cannot by itself create an equilibrium state. There always has to be multiple forces adding up to zero. As review from what we did last time. Feel good? All right. Last thing, tiny bit of math for this particular question. Which of the forces listed on our diagram there can we calculate a value for? Which value was given to us? Fg. We know the weight of the vehicle is listed here at 10,000 newtons, not pounds, but newtons. That is the weight of the vehicle, and weight is a synonym for force of gravity. If I haven't defined that in specific terms yet, weight is force of gravity. That is the definition of what weight is. Weight is the force of gravity. So if something weighs at 10,000 newtons, that is Fg. So we were given this one. Any of the other three, are we able to figure out with the information provided? Yeah, we can make some conclusions about normal force because we know the weight of the vehicle. Now I mentioned, we know every force here must add up to zero, but I mentioned that you can't add x to y directly, correct? Under no circumstances should we take all four of these forces, lump them together in the same line because they're in separate axes. So technically the net force calculations should be done once for the y forces and once for the x forces. When we look at the y ones, there are two y-axis forces acting on this car that we found. We got normal force up, gravity down, and again, net force is just the sum of all the forces. I've got net force y written here just to indicate we're going to take the two y forces and add them together. And we also know, because we defined the car as being in equilibrium, we know that whatever those forces are, they must add up to 0. So even if we didn't know how much the car weighed, the sum of these two things would still be 0 for this vehicle because we've determined it's in equilibrium. Now, if two things add up to 0, what does that usually tell you about the relationship between those two things?
Cancel out.
They cancel out. Mathematically, I'd call them equal but opposite. So to just quickly prove that mathematically, we don't have a value for Fn yet, but we do have a value for force of gravity. Again, 10,000 newtons. And I'm making that number negative because it points down. We care not only about axis, but also about direction within said axis. I'm usually going to call down vectors negative and up vectors positive. So I've written it here as negative 10,000. And once we plug that in, we've only got one unknown left. Algebra tells us we can rearrange to solve for that. So what then should normal force be equal to in this case? Perform a little bit of algebra here. 10,000. Specifically though, positive 10,000. Because to get Fn by itself, we have to add 10,000 to both sides. So normal force is positive 10,000 newtons, proving again that it is not only equal in magnitude, but opposite in direction. Gravity points down, normal force points up. And that is why they add up to 0. They're not just the same number, they have opposite directions, opposite signs. So, in this scenario, we can get to a normal force even if we weren't told what that normal force is. Does that feel all right? Just as kind of a math proof. Now this will typically be the case whenever an object is not accelerating up or down while it is on a level flat surface. Normal force and gravity are not guaranteed to be equal but opposite, but they will very commonly be equal and opposite if they are the only two forces vertically and they add up to 0. As the course goes on, we'll find scenarios where they are not equal and opposite, but they will very commonly be equal and opposite. Now, can we do something similar with engine and normal, with the friction force and the engine force right now? See a couple people gently shaking their heads no, and they are correct. Now we can set up some analysis of the x-axis like we did the y-axis. We know that the force of the engine forwards plus the force of friction backwards must add up to 0, but I kind of specifically left out any information about those numbers in the prompt. So that's kind of as far as this equation goes. We know they add up to 0, but without one, we can't find the other at this particular time. So that's the point of this question. We can get here, but it's okay that we can't get any further right now. As the course goes on, I'll tell you how to calculate this manually, and then we can work backwards to get force of the engine later. But once again, whatever they are, if two things add up to 0, they must be equal and opposite. So for a car to move at constant velocity forwards, the engine has to be canceling out with friction backwards. And that is again what the cruise control system in a car does. It calculates just the barely most amount of engine force that the car has to generate to mitigate friction backwards and keep you at the same speed. And if you don't have cruise control on, you just have to kind of do that manually with your foot. So, overall, how we feel? All right. With that, we have wrapped up all the things that the textbook kind of arbitrarily calls Chapter 2. Now, we are currently still studying the laws of motion. This has all been an examination of Newton's first law of motion. But at this point, we're now going to very slightly switch gears as we enter what is called Chapter 3 and describe motion in general rather than just the forces that can cause motion. So this is technically a separate set of notes. They are uploaded to Brightspace already. But it is a direct continuation. We're going from the laws of motion to describing motion specifically now. We want to be able to define the terms that we use to describe motion. Off the top of your head, what things do you think you can measure about the motion of objects?
How far it travels.
How far it travels, distance or displacement, very good.
How fast it travels.
How fast you're traveling, very good. Anything else?
Direction.
Direction's important. Direction is factored into the two vector measurements already mentioned. The third thing that we're going to be measuring and describing in this chapter is, we already said how fast you're moving. The third thing is acceleration, the change in how fast you're moving. So those are the three things we're going to be describing in what is labeled as Chapter 3. Now, kind of one tiny vocab word before the rest of the vocab words. This chapter is called linear motion. Linear just means in a straight line, of or referring to straight lines. It's literally line R. So the thing to note about this section is the types of motion we're describing right now are just moving backwards and forwards in straight lines. One-dimensional linear motion. We live in a three-dimensional universe, meaning that objects could be moving forwards or backwards in the x-axis, forwards or backwards in the y-axis, or forwards and backwards in the z-axis. It's kind of hard to draw z on a flat plane, but that would be, we have x, y, and z. And we're just going to start off with one axis at a time. We're not going to try to figure out 3D motion, 3 axes at once. We're just going to do one axis, forwards and backwards at a time. Could be back and forth, could be up or down, but just one axis at a time. Eventually we'll look at a few forms of two-dimensional motion. We're just going to start with one-dimensional. So that's either linear motion or 1D motion. I'm going to use those two terms interchangeably. Just wanted to make that clear at the front here. So, questions thus far? All right. So, I mentioned that there are three main things that we are going to be measuring and defining in our descriptions of motion. You guys mentioned displacement, velocity, and then also acceleration. So let's define all those things in terms of how physicists use them. First form of motion that we measure is just displacement, the distance but also direction that an object travels through physical space. The change in position from point A to point B. Now in physics, we like vectors because vectors have directions, and the direction is often very important. I would say when talking about motion, direction is very important because if you need to figure out how long it takes you to head north, it's kind of important to know if you're heading north or not. So for that reason, we like direction in physics, and that means that we try to use variables that contain direction as often as possible. Throughout your math and science careers, you have measured things both as scalars and also as vectors, and sometimes the same basic principle can be measured with or without a direction. If I ask you just the length of this line that I've drawn, length doesn't usually have a direction involved, right? It's just how long is this line? The same is true for the word distance. Distance is considered a scalar measurement, because it's just the physical space between 2 points. And so you could measure this line and say it's 1 meter long, 1 meter of length between these 2 points. This isn't exactly a meter, but just for an example. But in physics, we want to specify direction wherever possible. And so the measurement that we like to use in here is called displacement. The definition of displacement not only factors what is the distance between these 2 points, but it also factors in the direction of travel. It is not only how far you have displaced from point A to point B, it also factors in the direction from A to B. So displacement is a vector. The definition of displacement is the vector change in position from, very specifically, A to B. If I was to switch the 2 positions here, like say I wrote the same distance of line, but I swapped the position of A and B, the displacement from A to B would point in the opposite direction. So vector displacement factors in not only the distance you traveled, but the direction you were traveling in. So when I say displacement, as a thing that I am measuring or that I want you to measure, that includes not just how far apart the 2 points are, but also the direction from start to finish. Because we care about that sort of thing. Now, for everything that we can possibly measure in here, I did promise I would mention to you what it is, what we measure it in, and whether or not it's a vector. So within the notes, I've got this explanation here. Displacement, the variable for displacement in any formulas I give you is going to be one of these 3 things, either d for displacement or x or y for specifically x displacement or y displacement. It's a little bit flexible. I'd say it's the most flexible one. Most other variables will always use the same letter. This is the one that changes the most, but it only ever changes for the sake of specificity, either specifically x or specifically y. So I just wanted to make that clear right now. Displacement is a vector, and we are most commonly going to be measuring that in meters. We like meters in here. Good, right so far? All right, let's get in a tiny bit of practice and to help further differentiate distance from displacement. We are going to walk a few specific distances back and forth. Say we're trying to work on our step counter for today. From our starting position, we are going to walk 20 meters forward, which I'll make right forward and left backward. 20 meters forward, followed by 30 meters backward, followed again by another 20 meters forward, and lastly, 10 meters backward. My first question is, what is the total cumulative scalar distance that we walked? What is the distance that our step counter would indicate?
80 meters.
80 meters. Because distance isn't a vector. Distance doesn't care what direction you're walking in. Your step counter just wants to know how many feet, miles, paces you walked in a day. It doesn't really care exactly where you went, usually because you start the day and end the day back in the same place. But going back home doesn't drop your step counter to 0. Now, separate question then, what is the vector displacement from start to finish of this particular journey?
0.
0, because we ended back where we began. Positive 20 minus 30 plus 20 minus 10 adds up to 0. We are back in the same position as we started. Your step counter doesn't care. Your step counter doesn't know that. But in terms of where you are in the universe, back where you began, that's an important thing to note. Especially if you're, say, navigating or giving someone directions. So when directions exist, we care about that and want to factor it in when it's important. So that's just the difference between distance and displacement, how we feel. All right. So displacement is an important thing to be able to measure, but we already said that there are several other ways that we measure and to describe motion. You already mentioned that how fast you are moving is something that important that we can measure. So the way that we will be often measuring how fast you are in this class is called velocity. I'm going to differentiate that from speed in a moment. Velocity is the measure of the rate of change of displacement over time. If you are displacing, if you are walking forwards, it typically takes you a certain amount of time to do so, right? If I walk 20 meters forwards, it takes me a few seconds or minutes to be able to do that. If I could accomplish that task in 0 seconds, that's not walking, that's teleporting. I'd like to be able to do that, but I haven't figured it out yet. Travel takes time in our universe, and that is true no matter how speedy you are. It takes even the flash a few nanoseconds to get somewhere, most of the time. For that reason, velocity, and all things like it, are described as your change in displacement, the total amount of travel, divided by the time it took you to do it. And you see this on your car's speedometer whenever you are going somewhere, because the speedometer gives you your current speed in miles per hour, which MPH can be rewritten as literally miles divided by hours, distance over time. Same is true for every unit of velocity like this, kilometers per hour, meters per second. It's always distance over time, how far you went over the time it took you to do so. If it ever takes 0 seconds, again, that's not running, that's teleporting. There's my eraser. So this is one of our first formulas from the course. Remind me, this is the second Greek letter that's popped up. What does delta mean when you see it in math?
Change.
Change in, very good. So, small list of translations over here. Sigma means sum of, delta means change in. For you to have a velocity, you have to be changing position, start here, end here, and it has to take a certain amount of time. So delta D, or delta X, or delta Y, is your change in position. So I'm going to rewrite this a little bit as position final minus position initial. A change in where you are from start to finish. If I'm playing football and I begin on the 50 line and I end on the 100 line, I've displaced 50.
And then delta t, excuse me, is time final minus time initial. Delta anything, you can put that letter in front of anything in math. Delta anything is always changing that thing, final of it minus the initial of it. You want to know the change that took place. So anytime you see delta in a formula, it could be rewritten like this. Questions thus far? All right. This is a different variable, a different measurement from displacement. So again, information about how we use it. The variable for velocity is going to be very specifically lowercase English letter v. A common trend in this class will be that me complaining that physics ran out of letters to steal a long time ago. We rated the English alphabet. We rated the Greek alphabet, as you can see. So because of the letter shortage, some letters are going to repeat themselves. That's why I need to be very specific about lowercase v for velocity versus uppercase V for voltage, which is not the same thing. So note the cases used in a formula. I'm going to try to be very specific about that. Velocity is lowercase v. It is a vector because when you're running, you are running in a direction. It is impossible to, all velocities have directions. Even if you are running in place on a treadmill, you have a velocity forward, it's just what you're running on is moving backwards. And we like to measure it in meters per second. I've been very specific about using the word velocity because kind of like the difference between distance and displacement, there is a difference between speed and velocity as physicists define it. Speed is a scalar. Speed is just the number for how fast you're going. That's what the speedometer in your car tells you. 70 miles per hour is all good to know, but that doesn't tell you what direction you're heading in. Velocity is the vector counterpart to speed. Velocity would say 70 miles per hour north. And since we like to have directions in here, we prefer velocity over speed. Sometimes you don't know the direction, sometimes you can't determine the direction. So it's not like we won't use the word speed ever, but we prefer velocity around here. Does that distinction feel all right? Okay. Now, let's get in a little bit of practice for this, as I further want to make sure that the different forms of speed and velocity that you will encounter make sense. First up, we're going to go over instantaneous velocity or instantaneous speed sometimes. This is simply the rate at which you are moving right now at the moment the measurement is taken. This is the sort of thing that the speedometer of your car is very good at telling you. It will tell you how fast you are moving right now when you are looking at it. So, let's say we are driving at a constant rate and we move forward 200 meters every single second. No, every single minute, pardon me. 200 meters every minute. What is your instantaneous velocity as this happens? Got our formula for velocity here. V equals delta V over delta T. We want to know velocity. Our displacement is changing by 200 meters every 1 minute. And I'm trying to be specific in writing this in this form, just to show how it works. We are moving 200 meters forward every 1 minute. So the relationship between start and finish is we are 200 meters ahead of where we were. So we can consider starting at an origin point of 0 and ending at 200 meters past that. I'm going to try to write it out in this form when possible because sometimes one of these might not be 0. And as for the time part of it, it takes us 1 minute to do so. We started our timer at 0 minutes and we ended 1 minute later. So if we pop this into our calculator, the -0s just kind of all go away. We'd end up with 200 meters per minute. That would be our rate of motion. And every minute, we'd move another 200 meters forward as long as we maintain this constant velocity. Now, we do like meters per second around here. So how many seconds are in 1 minute? Bless you.
60.
60. Again, I'm not a trick. So if we instead did meters over seconds, we would get 3.3 repeating meters per second. Meaning every single second, this car moves 3 1/3 meters forward. And again, the direction here would be forward, because the only direction that we were given was 200 meters forward. If we're displacing forwards, our velocity vector also points forwards. The velocity inherits the direction from the displacement. So if you're displacing north, your velocity also points north. Or it might not be a very specific direction, but it's the direction we have. Feel right thus far? All right. Now, instantaneous speed and velocity is slightly different from average speed, which I'm not going to cover average speed very frequently, but it does come up from time to time, and I want to make sure that you're familiar with the difference. The definition of average speed is the total distance traveled over a certain total amount of time. So it's a slightly different formula. Is everyone okay if I erase this? Bless you. Slightly different formula. Average speed is total distance over total time. Average speed is not, and this is the main reason I'm bringing it up, is not the average of your speeds. So, looking at this example, you drive 40 kilometers in 1 hour, 30 kilometers in half an hour, stop for a 15-minute lunch break, and then drive 100 kilometers for the next 1.5 hours. That is your average speed. To find the average speed of this trip, just kind of to mirror how a common drive might go, because you're not always moving at the same speed. Sometimes you're on a town road, then you're on a back road, then you stop, and then you're on the interstate. To find average speed, you do not take those 4 numbers and literally average them. You do this, total distance over total time. It's a slightly different formula. The total distance driven would be 40 plus 30 plus 0 plus 100, the 0 being for the moment in time we were stopped. And the total time that this whole day took was 1 hour plus half an hour plus 15 minutes, which is a quarter of an hour, plus 1.5 hours. And that would be the average speed, not the average of all the speeds. Not something we'll do very commonly, but again, I wanted to make sure that I've defined this at some point. If you do this right, I believe your calculator should spit out about 52.3 kilometers per hour. We can just leave it in that unit for now.
So we're mostly going to be working in terms of instantaneous velocity. Any questions for any of this information? Yes?
How'd you get that 1/2 worth?
The 1/2 is the half an hour, operating in units of hours. So the 1/2 is the half an hour, and the 1/4 is the 15 minutes. Welcome. All right. Anything else in your minds right now? Okay. Let's do one more practice thing for in relationship to instantaneous velocity before we head towards the end for today. So slightly different question. We're going to drive for 30 minutes at a speed of 70 miles per hour. And then, as the speed limit changes, we will drive an additional 40 minutes at 60 miles per hour. And I would like you to tell me how far we drive in that lump sum of 70 minutes. How far do we travel over this whole thing? Yes?
75.
Yes, it is. Yes, it is. It is 75 miles. To prove where that would come from, we've got two different instantaneous velocities listed here. So I'm actually going to use this formula twice to find two different displacements and then add them together. First, again, I'm going to do this twice. So V1 is delta V1 over delta T1. 70 miles per hour. Solving for our first displacement. That took 30 minutes, but I'm working, since our velocity is given in miles per hour, I want the time unit I'm using to match the hours in there. So instead of 30 minutes, I'm actually going to put in 1/2 for half an hour. In order to solve for delta D1, how would you get this out from underneath? Multiply by what? Very good. Multiply both sides by 1/2. So 70 times 1/2 equals delta D1. And that would be 35 miles for this first section. 70 miles per hour for half an hour, 35 miles. The second leg, same process, but different numbers. Velocity drops to 60, and we do that for 40 minutes. Instead of 1/2, that would be 2/3 of an hour. So 60 times 2/3 equals delta D2. That would be 40 miles. And so the sum of those two distances is 75. So that would be the distance traveled across these two intervals of time added together. How are you feeling? questions about where 1/2 and 2/3 came from? Alright, we're about out of time, so the last thing I'll do is just show off the definition for accelerations, where we'll pick up for next time. We've talked about how far something can travel, we've talked about the rate at which you travel, but there is one more aspect of motion that we are able to measure, and that is the rate at which your motion, your velocity changes. Because you're not always moving at the same speed, and in fact, it usually takes you time to change your speed, to build your speed up, right? When you're driving and the light turns green, you don't hit the gas and immediately start moving at 60. It takes a second to get there, right? A lot of car commercials will talk about how many seconds it takes a vehicle to get from 0 to 60 miles per hour. At least it comes up on racing shows. And since velocity changes, we want to be able to measure that rate of change. That is what the definition of acceleration is. So just to set up what we're doing next time, we're talking about acceleration, the rate of change of velocity. If velocity is constant, you're not accelerating. And that was basically all of what chapter 2 was. If your motion is not changing, constant velocity, either at rest or at something, at constant something that isn't 0, in those situations you are not accelerating. So at equilibrium, net force is 0, no acceleration is happening. Acceleration happens when you break equilibrium, when you have a net force pushing you in a direction, forcing your motion to increase in that direction. When you hit the gas in your car, you increase the engine force forwards to make you accelerate and speed up forwards. But the main thing I want to go ahead and mention now is that acceleration doesn't have to mean it gets faster. Acceleration can include slowing down, because slowing down is still a change in your velocity, correct? Some people will call it deceleration, you're right, that's not a bad word to use for it, but within physics, the word acceleration can still be applied to both. Because physics just defines acceleration as a change in velocity that includes slowing down. And that's what we'll pick up next time. Questions for right now? All right. If you need anything, make sure to look over the homework and finish chapters. Please have a wonderful day. I assume because the note is here that the students running them have begun doing them. Usually they will come in here and write on the board if they aren't meeting for a certain week. But as long as that's here, it should be in session for the semester.
Okay, have a good day.
You too.
Can we start live today?
Yes. You don't have to prep anything ahead of time though, you just show up.
Okay. I'm sorry,